Hello everybody, my name is Elisa Baum and I'm Percona's Director of Product Marketing. We will begin in just a moment, but first I'd like to conduct just a bit of house cleaning. If you could please raise your hand using the hand icon located in the GoToWebinar control panel to let me know you can hear me, I would really appreciate that. Thank you. I see hands. That's perfect. Okay, I know I'm sounding at least loud. That's great. Next, during this webinar, you will be on mute. Should you have any questions during the discussion, please enter them in the questions field within the control panel. At the end of the webinar, we will take as many questions as possible. And those that aren't addressed, don't worry, they will be answered in a follow-up blog post entry on Percona's MySQL performance blog. In addition, I will make sure that each and every one of you get a recording of this webinar in addition to the slides within 48 hours. With that said, I'd like to thank you for attending today's webinar, How to Avoid Common but Deadly MySQL Development Mistakes, presented by Bill Carwin, who has been a principal MySQL constructor and now is a member of our Percona support team. In addition, Matt Griffin, who is Percona's Director of Product Management, will be joining Bill for the questions and answer part of our show. With that, I'd like to turn over to the floor to Bill. Bill, go ahead.
Thanks, Elisa. Can you hear me all right?
You sound great.
I'll assume so. This is the talk that I wanted to give on avoiding common but deadly MySQL development mistakes. We did a similar webinar a couple of months ago on operations mistakes, but this is a similar topic. I've been supporting MySQL users and database users for a long time, both on the for Percona and online at various forums like Stack Overflow or the MySQL forums, and I see very common mistakes done over and over again. Sometimes these are done by inexperienced developers who are coming to programming early in their careers or just adopting MySQL or SQL programming. But they can also be done by intermediate skill level or experienced developers, because they're cutting corners. That is, they're running into problems because they're trying to work at high speed, be very agile, and they're skipping some of the best practices steps, and we'll see some examples of that. And finally, there could even be cases where we see problems caused by people who are quite experienced as developers, but they're just unaware of some of the lesser-known internal behavior of MySQL. Every technology product has some kind of idiosyncrasies that are lesser known and which we can run into and get into trouble by avoiding. So here's a few of them to lead off with. Left join for everything, functions on index columns, and SQL injection. These are things related to query design, that is, as you're constructing queries. Let's talk about left join for everything. Just as a refresher, because I frequently see people who have misunderstandings about which type of join is which, the default type of join in SQL is just the inner join. And I'm trying to illustrate these. If you've got rows in table A and table B, you do an inner join between them, the center one in this diagram. It'll only find rows for which there are matches in both tables that match each other. On the left, left outer join is where we want all the rows from table A, whether or not they have matching rows in table B. And where there is no match, the A will still be returned, but the B will be as though all the columns are null. So I'm representing that by those white gaps, as though there's no matching row for B, but we still want the corresponding A row. And right outer join is just the flip of that. Right outer join is where we want all the rows from table B, but where there is no match, give us nulls as in lieu of table A rows. So that's just just to make sure that we all have a common understanding of that. One of the details about the MySQL Query Optimizer is that it can reorder tables. In spite of the fact that you listed A join B in your syntax of your query, MySQL may choose to access table B first. If it thinks that it can find the rows from table B more quickly, and then find the corresponding rows from the other one. So internally, and as a quick step before it actually begins executing the query, MySQL will perform this optimization automatically. In many cases, this provides a very significant speed up to your queries, and it's nice that it does it automatically. This works because the default join operator, the inner join, is commutative. If you remember algebra, you remember that commutative operators can give you the same result if you flip the order of the operands. So here's an example. We have projects and employees in our organization. Projects join employees gives us only those projects who have employees and only those employees who are assigned to a project. And we get the exact same result if we flip the order of the tables in our join, employees join projects. This allows MySQL to do the optimization that I described, where despite the order that you give the tables in your query, it can change that order and read them in a more efficient order. When would it do this, for example, if you were trying to look up rows for a specific employee? If you got a where clause to search for just the employee corresponding to Bill, it would look up that one, find the one row, and then use that to look up the subset of projects associated with Bill. And that's the case where it could gain a benefit from that. The outer join is not commutative. If you change the order of the tables in that join, it has a very different meaning. Projects, left outer join employees, I'm treating the outer as an optional keyword. It's you can put it in there or not. So projects left join employees would show you only projects, even those with no staff assigned. Whereas employees left join projects shows you all employees, even if they aren't assigned to any project. And therefore, the query optimizer can't feel free to change the order of the tables. It's going to access those. Putting the table on the left, in this case, means that it's going to have to scan the entire table regardless of whether there are any matching rows. And then for each one of those rows in the left table, it'll look up any of the corresponding rows on the right. So you've just lost the ability that the optimizer was going to give you for free of trying to read the more efficient table first and then look up on the right. Where this comes up as a developer mistake is that I see people who don't understand the different uses of the different types of join, and they just use left join for everything. And I frequently see this happen in questions online where people have a 6 or 8 table join and they just say left join for everything, even cases where it really shouldn't be because it's a foreign key to primary key relationship, so by definition there cannot be an unmatched row. This gets even more confusing because there's a case where there's an exception to what I described. Take a look at this. This is another mistake that people make, although it doesn't have a high impact. If I've got a where clause following my join, where I'm actually comparing one of the values in the outer table, that is the right table in that left join, to a specific value, that cannot be an expression that's true for any of the null rows that would be represented by an unmatched employee. Therefore, it only returns the rows where there's a project and an employee with non-null rows, and therefore it makes this join work like an inner join. The left join there would be superfluous and would actually be factored out by the optimizer. I did test this, and it turns out that it really does optimize like an inner join. It can then gain the benefit of table reordering. But it's confusing because this depends on whether you have conditions in your where clause on that table or not. If you remove that condition in the where clause, it resorts to what I described before, where it defeats the table reordering optimization and goes back to function like an outer join. So be aware of this. Use the right type of join that corresponds to what you need for the logic of your query, and practice. Make sure you have in your mind what the effects of those different types of joins are. Here's another mistake. Functions on indexed columns. Let me show you an example of what I mean by that by first showing you why indexes work is that the index is a sorted copy of all of the values in that column. If I'm looking for a specific date, for example, in this date column, in this query, it knows how to find that very quickly. It can narrow down the search to just the date by the fact that it can look up those dates in that sorted list. It's a very efficient way of doing that. But what if I'm doing a query where I'm just looking for rows matching a given month? The month appears in the middle of a date. MySQL dates are always year, month, day. So trying to find those months that are all corresponding to April would naturally only be able to do that if it could scan through every distinct year. MySQL won't do that because it doesn't know if it's going to have to scan through a few or many distinct years. And in this case, when you put a indexed column inside of a function like this, MySQL's optimizer gives up and says, I can't infer that I'm going to be able to use the index for this case, so we're just going to fall back to the hard way, that is doing a table scan. And this happens with a wide variety of the functions that you could use. There could even be cases where we would look at a query and reason, oh, you should be able to use the fact that the index is sorted by alphabetical order. Here's a case where I'm looking up in a text column and looking for the first 3 characters, which should be in the same sort order as the whole string. And looking that up should be able to use an index. However, I tested this one and MySQL's optimizer still doesn't use that. It seems that every usage of a function is unknown to the optimizer, and it just assumes that it's going to be unable to rely on the index order to do that lookup. There are some cases that are optimized, like other predicates such as like or in that can do range scans, but for functions it doesn't do that. In some cases you can refactor your expressions and make sure that the column is isolated on the left side of the comparison and it's only comparing to a constant value. But in other cases it's not possible to do that refactoring. And for those cases the only workaround is to denormalize. For example, if we wanted to look up those values by month, we could copy the month value into an extra column. In this example, I'm adding a column called month. It'll be a tiny int. I scan through the whole table, setting that column to be the result of the month expression on date column. I only need to do that once, and then subsequently, if I ever change the values of the date. Now I can look up a in that table where a month equals 4, supposing we had an index on it, and it will function much more efficiently. No description of common developer mistakes with SQL would be complete without mentioning SQL injection. This is a security threat. This is not for performance, but it can be certainly a performance killer in that it can bring down your whole company if this happens. It's consistently the top web app vulnerability. Many of you have probably already heard about this. I've even been reading reports in the last week that major Bitcoin market, Mt. Gox, has been rumored to have been compromised by SQL injection, and the perpetrators of that may have gotten away with many millions of dollars of Bitcoins. So this is serious. To refresh everybody's memory, what is SQL injection? It happens when you gather untrusted variables or input, typically user input, but really any untrusted variables from any source, and interpolate them, that is, copy their values directly into strings that you're preparing for SQL. Here's an example where we have a query select from users where user ID equals, and then this is a PHP example. We're using the PHP superglobal inputs, get. So these are values that are being provided by the user as part of the HTTP request. And even if we use strong hashing for our password storage, we can still get cases where people can sneak in untrusted input. An example, if somebody were to pass in a Boolean expression and then terminate the rest of the query by putting a comment character, the double dash, what's the effect of this? Now they can get access to the that login for that user without having to provide the password at all. And this is a very common form of SQL injection, but we won't go into a lot of detail about other types. Solutions. If you have an expectation in your application that a given input is going to be of a specific format, like an integer, make sure that it's an integer. Use variable coercion or typecasting to remove any non-numeric characters. You can use something similar for other types like dates and floating point numbers and so on. Other solutions, make sure that any other characters like quote characters are escaped. That every database API in every language provides some function for doing this. Here's an example from PHP's PDO library that has a function called quote that puts in backslashes in appropriate places to make sure that you can't artificially terminate a string. Even better is to use prepared statements. They're pretty much equivalent in level of security, but I find them easier to use because I never need to worry about whether I've escaped a value or not. In fact, if I do try to escape and put backslashes in, they'll creep into my database as literal backslashes. So don't do that. Just treat the value as verbatim its input, knowing that the query parameter substituted in for this question mark here is unable to compromise your SQL query. But there are still yet other cases where escaping and quoting don't help. For those, I use whitelisting. So if I've got an input that must match a limited set of values, for example, if I'm going to be allowing the user to choose which column by which to sort, I can use a whitelisting mechanism. And here's a simple way of doing it. Use an associative array in PHP indexed by the columns that you have. Then I can use the application input. The $get sort by would be the name of a column. If that entry exists in my columns array, then use it. Otherwise, or else, use a default like ID. Therefore, I know that I've filtered the input. If somebody tries to put in something that is not one that I've identified as a legitimate column in those array keys, it'll default to the ID. They can't put in anything that's unknown to my application. That's a very brief summary of techniques for solving SQL injection. We've talked about this quite a bit on our blog and in past webinars, but if you have any other questions on that, I'd be happy to point you to some of those. Some of the other mistakes we see for database design, one I call premature denormalization. I heard denormalization makes web applications faster, so I'm going to use it as much as possible. But that's a very simplified way of looking at it. Normalization of databases helps us to do data modeling, and the purpose for data modeling is not to achieve performance, it's to avoid data anomalies. That is, making sure that every piece of information is stored once so you can't get redundant copies that get out of sync with one another. Denormalization breaks those rules that guide us to do normalized databases, but it does so carefully and judiciously. And the reason that we do these is for the performance of specific queries. Let me show you some of the scenarios we'll do in a moment. Why would we not denormalize as much as possible? Because every time you do this, every case where you store data in two places in your database, it increases risk. That is, you could have applications that are unaware or have not been updated to make sure that those redundant copies of data stay in sync, and therefore they will eventually creep into situations where you have data that doesn't agree with the rest of the database, and that becomes a difficult task to try to clean up. Which one of these copies of the data is correct? So for example, I changed my email address in one place, but it didn't change it in the other place where it's stored. Which one of them is the current one, and how do I clean that up, and who gets to decide? If your applications don't take care of that automatically at the time that the update occurs, then you have a reconcilable difference. Another reason why not to denormalize is that the denormalization is done for the sake of performance of one type of query, but it frequently tends to hurt the performance of other types of queries. Having a redundant copy of data in one place makes it so that you can access it quickly, but the extra performance required to keep those in sync or to search for anomalies causes performance problems in other ways. When to use denormalization? Use them in cases where you can prove that the benefits justify those risks. If you're willing to do the work to make sure that the data stays in sync, it better be because you have identified a specific case where you need it. And identified and specific have to go along with testing. Being able to test and make sure that you can demonstrate that in a quantitative way is key. So some of the types of denormalization. One would be to create an extra column for the result of expressions to avoid recalculating it every time you do a query against that table. For example, you might have a shopping cart where you store the total price of what the user has purchased, which would be the unit price times the quantity. To avoid doing calculations like that every time somebody views the contents of the shopping cart, you could store an extra column with the result of that multiplication. And that's a simple example, but you can imagine that there are expressions that are even more costly than simple multiplication, and you'd like to save the results of those expressions, even though they are technically redundant because the components of that multiplication are already stored. And also the example we gave earlier of storing the month to allow us to do searches on month in a given date expression. So trying to copy values out based on the result of a function on a column so that we can index it. Creating an extra column for aggregates is another case of denormalization to avoid doing group by queries. For example, maybe we have a movies database and users have given ratings to movies. Trying to show the movie, which would be a common thing for this application to do, would include the average user rating for the movie. But do we do a group by query with a lengthy scan of the user votes table to user ratings table to see the average user rating for that movie? That would be pretty costly. We'd much rather store a numeric column associated as an attribute with the movie so that we can recall it quickly without having to do that group by query every time. Some people call those summary tables, the results of set-based functions like average, sum, count, max and min, things like that. And finally, a column that's a clone of a column from another table. And the purpose of this is to avoid doing a join. For example, if we wanted to copy the product name in addition to just the product ID so that in a shopping cart we can have quick access to that string and be able to display it. To the alternative being to do a join every time we want to display it. So those are three basic categories of denormalization. Always creating redundant data, but for different purposes, to avoid an expression, avoid a group by, or avoid a join. Another database design problem, VARCHAR 255. Why do I have a problem with this? It seems like a good de facto choice for anything that's going to store string data. In fact, many people use it for that. If they don't know what the longest string they need to store in, say, for example, a street address or an email account or a URL, they may just say, well, what's the longest varchar that it'll permit? And I'll trust that varchar will store it efficiently. You can declare a varchar up to 64 kilobytes, 65535 bytes. And included in that is either 1 or 2 bytes, depending on the length of the varchar you declare. If you restrict yourself to just 255 or less for the length, you only need 1 byte to encode the length. This is all internals, things that are happening internally. We can be assured that varchars are stored compactly on disk. That is, if you put a short string into a varchar 255, it only takes enough space to store the string that you actually specified. It doesn't have to actually store all the bytes for the rest of the 255 characters. And that happens on disk and as the storage engine buffers things, like the InnoDB buffer pool. But as the string comes out of the storage engine layer and into the SQL layer, that is, gets prepared to be part of the result sets of your queries, gets sorted, gets put into formats that are independent of storage, it pads out those lengths. It wants those rows to be of fixed length, and therefore it needs to allocate as much memory as would be used by the longest string that could be stored in that column. So it uses all those bytes. And remember that in order to account for multi-byte characters, it actually allocates extra memory for UTF-8 or UTF-8 MB4. So a varchar 255 in UTF-8 would actually occupy 765 bytes in memory, regardless of the actual entry that you put into that column. This makes that design very inefficient if you typically use strings that are short. And in fact, there are many cases where I've seen varchar 255 used for columns that could never be that long. Here's some example. Postal codes. They're short. They're never going to be anywhere near 255. IP addresses when stored in a string format. Even the longest format for IPv6 isn't anywhere near 255 characters. And MD5 hashes are a fixed length string of hexadecimal digits that will never be anything else other than that. And there are many other examples. I'm just showing you a few. So we need to think about this a little bit and realize that there are some costs to just over-allocating the length of that varchar. For example, if you've got a postal code column, do some research. It doesn't take long to figure out what the various formats of postal cards are, even for different countries, and decide on a more sensible varchar. Sometimes that's difficult to do because you don't know if you're going to encounter greater lengths in the future. For example, what's the longest name that somebody could have? Well, it depends maybe what country you're from. So you could over-allocate a bit or overestimate to give you some extra room. But 255, that's probably way overkill for somebody's name or even a street address. Storing text in a binary column. This comes up with the choice of character sets. Character sets are the way that we store international characters or extended characters. And really, characters in any format are just come down to storing bits in a byte. And how that maps to actual characters is based on the character set. We can show that by looking at an accented character like the E grav that, or E accent, with two different ways of storing those in different character sets, Latin 1 and UTF-8. And then I'll convert those back into the hexadecimal strings that correspond to the bytes. Looks like Latin 1 uses a single byte hex code E9. UTF-8 treats this as a two-byte character C3A9. So depending on the character set, a given letter could be interpreted as a different bit pattern and even a different number of bytes. You can declare a string column with no character set. There's the character set binary, so it's not going to apply any of those interpretations or mappings between bytes and characters. It's just going to store the literal bytes themselves. So here's a case where I did that, created a varchar character set binary. And if I insert this data in there, we'll see that happens in a moment. When you do this, there's no associated character set associated with the data, and therefore the application has to guess, really, how to map the bits into letters. And it may not be getting it right because you may have stored strings in one character set corresponding to one set of bytes. The application makes an assumption and gets the bytes out and tries to apply them to a mapping that's the wrong mapping, and you end up getting garbage characters. Here's an example where I used that varchar with binary character set, and I stored Latin 1 and UTF-8 characters into it, noting which one is which. And it looks like the UTF-8 went in okay for this, or at least it got interpreted correctly as we fetched it back out because my session was using UTF-8 as its default character set. But the Latin one, it has no idea how to map that. It doesn't map into the correct value in UTF-8, and it just turns it to a little question mark as a placeholder. It even throws off the formatting of my result set by adding some extra space there. We've run into this quite a bit at Percona support and had to help people to clean up their data when they inadvertently defined a database with no character set and then stored character set data into it. Or even, as I did in this example, stored data from two different character sets accidentally into the same column, which really messes things up. And it's hard to clean up. So the solution, the better practice, is if you've got textual data that you want to store in a string, be sure to store it with a appropriate character set for any and all string data that you want to be interpreted as characters. Here's an example where I created a second table. I declare a default character set UTF-8 MB4. This supports the full range of UTF-8 planes of character mappings for extended characters in lots of other languages and locales. When I insert those strings using Latin 1 or using UTF-8, it converts it into the appropriate character set for the storage, and therefore despite using Latin 1 for one of them, it's actually converted it so that it's storing it consistently with the other characters. That can save you a lot of grief later on. How about application design? A few different cases of these. See no evil. This is sort of a joke name that I apply to this mistake that people make. Say, for example, we have this code. I'm treating this as PHP just because it's a common language that many people use, but this could occur in many different languages. What's the error here? And if I actually try to execute this, this PHP code, I get a fatal error when I try to fetch the result of the query. And it says something cryptic like calling a method on a non-object, which is not very helpful to a new programmer. I see this type of error and question come up very frequently online with people running PHP. So what is the, probably many of you have already spotted it, but many of you may not have. If I were to actually look at the string that I had constructed from in that previous slide, I noticed that there is a mistake where I had forgotten a space in between the table name and the where clause. That is, I concatenated two fragments of HTML of SQL together with a string concatenation operator, but both of the strings individually quoted had no space inside them. So this is a case where it's very easy to make this mistake, run things together where there needs to be a space in between them. Any statement can have errors. You could have syntax errors like this one, where I just ran two words together and formed an invalid query. You could have reference errors. That is, maybe you misspelled a table name, and or had the SQL query that at one time had the correct table name, but then somebody renamed the table later on and broke your query. Maybe you got everything right, but you have privileges errors. You just don't have select privilege on that table, and therefore you can't read from it. Or semantic errors. Maybe you've done an ambiguous query and you're in a strict SQL mode so that it can't actually execute it. Otherwise, it's syntactically correct and privileges-wise correct. Just you're trying to do something that SQL can't do, like an ambiguous group by, or doing a limit on non-numeric arguments, or some of the other types of cases where it's ambiguous. Trying to track down errors like this can be tricky, and you have to make sure to test the result of your queries every time you prepare one. It means writing more code. It means writing some code that after you do the query, test to see if the result is indicating a success or a failure. It's common in the PHP libraries, for example, for the result of a query to be the literal Boolean value false if there is any type of error associated with that query. You can't call a object method on a false value. So if result is storing false and we try to call fetch on it, that will be a fatal error and it will complain at us. It has to be an object to have a method. I remember on one occasion when I was supporting a customer years ago, not at Percona, he refused to do this type of error checking, and he asked us, he said, if there's an error, then it must be the result of a bug in your product, in your database product that I was supporting. Therefore, I should never have to do that because you should have no bugs. And he was pretty strict about that statement. So I tried to help him debug a situation that he was having, and I finally convinced him, just as a test, to display the error message in case there was a problem with the query preparation. And it said, select, command not found. He had literally just misspelled the word select in his query. And I convinced him that there are ordinary circumstances where you need to do error checking every time you do this. The analogous situation could be you're just trying to open a file. You could have the file name spelled wrong. You could have the permissions wrong on the file so you can't open it. Somebody could delete the file before you open it. You always have to test to see if the file open was successful. And the same is true of SQL queries and many other APIs as well. This may seem like a lot of extra coding to do, but you could use exceptions to try to minimize that. Many of the database APIs in different languages will throw exceptions on their own, so you don't need to write extra code to detect this every time. Just configure the database interface to throw exceptions. Both MySQL and PDO in PHP, for example, have options to do that. And other languages may do it as a default thing, like Java and Ruby and Python that are accustomed to using exceptions. Another development mistake, N+1 queries. This is an interesting case because it hides from us. Say, for example, we're using an object-oriented framework for our development, and we can query to get a parent object and then iterate over dependent objects. For example, I'm looking at the contents of a shopping cart, and I say, for each cart, get line items, looping over it with a loop variable item. I could echo, I know that the get line items function internally is using an SQL query to get a list of the line items associated with that shopping cart. And those items may have attributes of them, like, for example, the quantity of how many socks we have in this line item of our shopping cart. We're buying socks. That's okay. The quantity is a scalar attribute of the line item, but if you've got dependent objects that come associated with that line item, for example, we want to get the actual product name instead of just the reference to its ID. Our framework may magically, behind the scenes, do that as a lazy query. That is, we fetch the line item, but to get the details of the product, it'll wait until we actually reference that product in an expression like the second line, echo item product name. And at that point, it does an extra SQL query. As we loop over all the items in our shopping cart, we end up executing a lot of SQL queries. That's where we get the N+1 name. We've done the +1 first to get the line items, and then for each of the N line items that we fetched, we do an extra query. So we've gotten N+1 queries going on. What happens is no big deal, but what happens if somebody happens to have a shopping cart where they have 1,000 items in their shopping cart and displays on the screen will cause a great deal of query load on your database server. This happens in unexpected ways. In some cases where I've designed a web application that I expected people to add a dozen items to their shopping cart or their order, and our quality control people tested this and they said, what happens if you add 10,000 lines? What happens to the application? And it causes an unforeseen amount of database load when that occurs. This is typical of object-oriented interfaces because the folks who designed the object-oriented interface, and even we as users of it, may assume that because it looks like we're just getting new objects and we associate a new constructor of an object to be a fairly inexpensive operation, that may work against our instincts. When in fact, instantiating an object by calling new is causing a database query to preload the data into fields of that object. The other way that object-oriented interfaces run into this problem is because they think of individual objects primarily as their first-class citizen rather than thinking in sets of objects. We'd really rather be able to fetch whole sets at a time because that's how SQL accesses data. So solutions. One solution I've seen in some frameworks is that they optionally allow you to preload related data. For example, here we say get line items as their method, but we also have this optional syntax where we can include a related table by telling it, oh, and this also joins to the products table, so please get that as part of the initial query. And that will eliminate the n+1 queries. It'll just do the one with a join, and therefore it'll all be ready. But we have to be able to predict that we're going to be accessing the product name and need to do that join in order to decide whether or not to do it. Another solution could be to, instead of calling new to get an individual objective each time, implement a static class method for products that we can pass a list of item IDs, and it will use a range query in a single query to populate a collection of instances of that object. So here's an example where we iterate over our line items, collect up all the product IDs, which may be a scalar attribute of an item, and then based on that, build up an array, pass it to the static factory method, which will return a collection of products. It did one SQL query to get all of them by the list of product IDs, and then populated them into object instances as a more efficient operation and returned the array of objects to us. And this would be something that we'd have to architect into our application to be able to do efficiently. So we'd be responsible for coding that get many, which would fetch all the raw data and then populate it into the fields of shell objects. Finally, stored procedures is another case. This might be a little bit controversial for me to call this a common but deadly mistake, but let me make the case for that. Stored procedures, many of you may have seen these. These are cases where we are able to write some code and actually have that stored in the database server. Therefore, we can call that code from SQL statements to supplement parts of our application where the majority of our logic is. We could actually have quite a bit of logic in the database doing SQL queries and manipulating data. Procedures can return a result set as though you called them as a select. They can even return multiple result sets, and we can loop over the result sets, each of which have multiple rows. So they have some capabilities that are kind of interesting. It's common in some projects to use procedures to encapsulate some of the logic for their database access. In some projects, even they have a policy that all the database access has to go through a library of stored procedures that they create for the project. It gives us the opportunity to abstract complex operations. If I have a procedure called empty shopping cart, I could call that procedure and it will take care of all of the data manipulation on the back end, because the person who knows the best steps to empty a shopping cart and to remove all those line items coded that procedure, and they know that they've done it well. You can even manage privileges. So maybe the other application users have ability to call the procedure even though they have no privileges to manipulate the table underlying all those data changes directly. And therefore the procedure can be a way of governing limited access so that we know that it's going to happen in the correct way. But there's some disadvantages to procedures. For example, performance. unlike in some other brands of database, people who are accustomed to Microsoft or Oracle or DB2 may be coming from a culture where they think of procedures as efficient because they're compiled on the server. They remain compiled until anybody needs to change the code for that procedure. Not the case on MySQL. In MySQL, the first time you execute a procedure in a given session, it parses it at that time. You can re-execute it within the same session, and it will reuse that parsed version. But that parsed version is discarded pretty quickly at the end of a session. And in fact, it's pretty typical to only execute a procedure once in a given session. Also, if any developer changes the code for the procedure, it automatically causes all threads to discard their parsed versions. Pardon me. Debugging is harder than it is with more familiar programming languages. There's not really a good solution for debugging MySQL stored procedures. There are some toolkits that I've seen that try to simulate debugging. For example, they insert logging statements and try to make sure to tell you what happened during a procedure. But using true debugging, that is doing stepwise cases, breakpoints, modifying code in the debugger, and things like that is not really possible. The language that we use for stored procedures in MySQL is also limited. It's based as close as possible onto standard SQL 2003 language, but that's a pretty limited language. It's not very sophisticated, doesn't have a lot of built-in structures. There's no packages for organizing your procedures. There's no object-oriented features like inheritance. And MySQL, unlike other brands of database, does not provide a standard library of reusable procedures or for system tasks or for developer tasks. It's really rather sparse. Scalability is another concern. Having a lot of procedures in code functioning and being parsed as you execute them on the database server puts a lot more CPU load on the database server. In some cases, I've observed a deployment where the project had many application servers that were more or less idle because they were waiting for calls to store procedures to finish. Whereas on the database server that they were all calling those procedures on, the CPU was pegged at 100%. Scaling out means spreading the workload over multiple machines. And if you have the capability of moving code onto other machines, that would be a better choice than to execute a majority of your application code on one machine, which is the database server. So move more code to the middle tier. It gives you some advantages, like if you're more familiar and facile and have good developer tools for your favorite language, whether it's scripting language or Java or something else, you have the opportunity to be more productive as a developer in that environment. You can still encapsulate your frequent database tasks if you write a library within your chosen language so that the majority of your database work is consolidated and abstracted from the perspective of the rest of the app. And the other advice is reduce reliance on stored procedures in the database. They're still helpful in some circumstances. I've seen stored procedures used well to try to make it more efficient to do multi-step tasks. If the alternative was we fetch some data from the database, we bring it into the application, we manipulate it in some way, and depending on that, we execute more queries, and then back and forth and back and forth. That's a lot of overhead to be copying data from the database to the application layer and repeatedly going back and forth. And that can become a bottleneck if you have those types of complex multi-step tasks. So the advice is, on those cases, yes, that's a good application of a stored procedure. It doesn't have to copy the data over the network because the code in the procedure is in the same process space as the MySQL daemon itself. And those are cases where the bottleneck can be solved very well by a stored procedure. But clearly, as I've described them, that would be the exception rather than the rule. That's it, what I've got for today. And I wanted to mention that I'm the author of a book called SQL Anti-Patterns, Avoiding the Pitfalls of Database Programming. It's been a very good, successful project for me. It was published in 2010, but a lot of the lessons in there are nice and evergreen. You find a lot of tips in there to help you in doing development. They're actually doing a sale right now on the hard copy version of the book, so you can go to that pragprog.com book/BKSQLA and see what the current prices are. And also, if you like all these sort of tips that we share at Percona all the time, feel free to register to come to our conference that's coming up next month, April 1 through 4. And it's by attending this webinar, you get access to this discount code, WebinarSC, to get 10% off of new registrations. Go visit that at percona.com/live. That's what I've got for today. Matt, do we have any questions in the control panel?
Yeah, thanks Bill. Yeah, we've got a few questions. And just as a reminder, if anyone else has any more questions, please type them in, and we will get to them as many as we can before the top of the hour. And any questions that we don't get to, we'll do a follow-up blog post on the MySQL Performance blog with answers. So the first question is related to join query performance.
Mm-hmm.
A join operation between two tables always produces an access table on the rows of the first table of the join, or is it possible to define an index, like a covering index, to avoid this access to the first table?
Certainly covering indexes are a really great way of optimizing queries, and we can utilize that sort of implicitly with MySQL. If the query that you're issuing is only mentioning a subset of the columns in that table, creating an index that includes those columns can allow the query optimizer to avoid having to touch the table or to access the table directly at all. It can get the answers that it needs to right out of the index itself. And for a analogy, I often think of a telephone book. The telephone book is sorted by last name first, first name last, so we can search by people's names. But in addition to that, what else do we find in each entry of the telephone book is the phone number itself. And that's something that wasn't part of our search criteria, but it's an extra column that that comes along for the ride. That's a very powerful way of organizing indexed data, and we can achieve the same thing with MySQL indexes.
Okay, and as a follow-up, do join operations always fetch the rows table access of the first table to do the join with the second table?
It would access the index entry first, and if it has enough columns in that index entry to perform the lookup on the second table, then it can do that. If you need a column from that row that wasn't part of the index, it would have to then access the table to fetch the row to get that extra column, and then use that to launch off of and find the matching rows in the second table. So it depends on what columns you have in your index, whether it needs to access that. That's, for example, compare that to Postgres, which until the recent release where they finally supported this, they could not do covering indexes at all, because they couldn't rely on the entries in the index being parts that you could see. They could only resolve that by accessing the table row. But MySQL supported that for a long, long time.
Okay. What about the performance drawbacks of prepared statements? Can you share some information there?
Interesting question. There's been some discussion about prepared statements as being a performance problem, and the reasoning goes that if I'm going to be accessing the database once to prepare the query and then a second time to send parameter values, that's 2 round trips. That is 2 contacts from the application to the database server in order to execute a query before I can get back results. But those claims that I've seen done on articles and blogs are usually done without actually measuring the performance. if you do benchmarking and compare those, you actually find that it's not nearly as bad as doubling the performance cost, unless you have some extraordinarily slow network, for example. In practice, it may be a tiny hit, but the additional benefit you get from using prepared statements is generally going to outweigh that. That is, it protects you for in cases of security, and it actually becomes a performance improvement if you are going to execute that statement multiple times with different parameter values. So I wouldn't worry too much about the performance impact of using prepared statements.
Okay. And back to your discussion of data types and character sets, what about using fixed length text fields rather than varchars?
The benefit of using a fixed length text field used to be important when we used MyISOM tables. MyISOM tables would be able to do a special type of optimization if the whole row was a fixed length. That is, all the data types, all the columns were a fixed length or fixed width, which means no varchars. You can only use integers, dates, and those types of things, and char, the fixed length string format. The optimization was that they could then treat the entire file as a series of fixed length rows, and therefore compute the position of a row as the multiple of a row size. This is not relevant to InnoDB, and we recommend InnoDB be the storage engine we use for MySQL tables going forward. MyISOM is more like the legacy version. InnoDB doesn't have this kind of treatment of fixed length rows. Everything is accessed by pointers anyway, so there's no more fseek into a position which is a multiple of a row size. That's never going to happen in InnoDB. So it's not a optimization anymore.
Okay, and related to that, for people that notice and discover opportunities to improve and fix some of these issues with data types and character sets and field lengths, do you have any advice on fixing some of these problems?
Fixing some of these problems, like if you decide on a better data type to choose for a column, it can be a little bit painful, because if we try to alter a table to change the data type, it may perform a table restructure, which can take some time if you've got a very, very large table. A couple of solutions to that. One is investigate MySQL 5.6, because they can do online alter table without locking in many cases that didn't used to be possible. So they've done a lot of interesting work with that. Read the documentation about the cases where that can be done as an online alter table. If you have a case that still can't be done that way, or if you're using an earlier version of MySQL that doesn't support the online alter table, there's a tool that Percona makes. It's a free tool called PT Online Schema Change, and it can perform many more types of online alter tables by performing the restructure in the background while it's capturing ongoing changes to your table and triggers and applying them to the restructured table in the background. There are also some caveats to using this, but in general it's been very successful to allow people to avoid the pain of changing a data type or adding a column or adding an index, and it does so by removing the requirement to lock the table while you're doing it. It's really a very good tool, and when I post a follow-up blog, I'll give links to all these things that I'm giving you for tips.
Great, great. We've got a few more questions, and I think we are nearing the end of the time. Those of you that have more questions, please feel free to submit them here, and we will address them in a follow-up blog post after when we make this webinar available for anyone to view as a rebroadcast. So Lisa, do you want me to hand it over to you?
Yeah, Thank you guys. Very good job. Everyone, thank you so much for attending today's webinar. As you know, I will make a recording available to everybody here within 48 hours. And as Matt said, if we didn't get to your question, don't worry, we will address it in a follow-up blog post. Bill will put one up there on MySQL performance blog sometime in the next few days. Also, next week, March 19th, our next webinar is Monitoring MySQL with Monyog, and that's going to be done by Peter Zaitsev, who is Percona's CEO and a founder and a rock star as well. So we look forward to seeing you on future webinars. And with that said, everyone have a fantastic day, evening, or morning, depending on where you're calling in from. Hope to see you again.